continue. Okay, so thank you everyone for coming to the third and last lecture of Professor Marcos Alexandrino. We're really glad to have him here, and it's a pleasure. Thank you, Professor. Please go ahead.
Thank you, Jesus. So today will be my last lecture. I try to maintain the lectures a little independent. In this way, if you someone lose one can understand the other. But of course, the others too has prepared us a little to understand what I will talk today. It will be based on ongoing project on this paper and on this other paper. So let us start by recalling a few concepts that we saw in previous lectures. So a partition of a manifold M in complete connected immersed submanifolds, the leaf, is called a singular foliation if every vector tangent to a leaf can be locally extended to a vector everywhere tangents to leaves. Okay, so if you have here, and if you have this vector, and if you have your foliation here, then you create vector fields that are also tangents to the other leaves. And this is includes then the definitions of regular foliation. Are You can define a regular foliation like that. I think it's even easier for students to understand. And it is called the Riemannian if we start with a horizontal geodesic to a leaf. If we start with a horizontal geodesic to a leaf, then it remains orthogonal. So this is what we call Riemannian, and it says essentially they are locally equidistant. A very nice example to have in mind is the partition of M into orbits of an isometric action. We saw yesterday another kind of example. So consider now will be a Riemannian manifold, A will be an Euclidean vector bundle. That is, for example, the tangent, think B as an embedded submanifold in Euclidean space. Then E can be the tangent space of B. E can be the normal space of B with the induced metric. And then consider the metric connections. Again, you can consider the Riemannian metric, the Riemannian connection, or the normal connections in those classical examples. Okay, and then you put a metric. We put a metric on this bundle. We put a metric on this bundle in order to make this. Just 1 minute. Okay. Yes. Then we put a metric on this bundle in order to make the foot projections a Riemannian submesh. So you have here the foot projections, and we put a metric here in order to make this guy a Riemannian submessions, and the fibers that have original metric remains with this metric. Then the holonomy foliation is a partition of A, where the leaves are declaring as follows. Two vectors belong in the same leaf if they can be connected to one another via compositions of parallel transport. Here was the picture. I fix a vector and start here. There are curves in our basis, and I started to translate this vector in all possible directions, this induces a submanifold that we will call the Aleph through V. The intersection of this submanifold with the fiber turns out to be orbits of the holonomy group. With the Sazak metric, this partition turns to be a singular Riemannian foliation. This is not difficult to see. Essentially, the Sazak metric implies that the fibers are totally geodesics. And since here we have a partition of a vector space into an isometric actions, these foliations here in AB turns to be isometric, singular Riemannian foliation. And since this guy is totally geodesic, an orthogonal geodesic here stay inside of this guy. So accepting the fact that with Sazak metrics, the fibers are totally geodesic, it's not difficult to check that this holonomy foliation is in fact a singular Riemannian foliation. So you always have a singular Riemannian foliations when you start to work with the Riemannian geometry. It doesn't matter if you use this term or not, they are there. They also are part of the life of people who works with the non-negative curvature in the non-compact space due to Sharot-Futinov theorem. The projections into the soul induce always a Riemannian submersions, and the dual leaves that are locally a kind of holonomy foliation are there. So Riemannian foliations are part of appears very natural in Riemannian geometry. In particular, if you are working with a non-negative, non-compact spaces. We use this example in particular, as well as the isometric actions, to illustrate those concepts of a slice. The slice was the normal space of a leaf. Here, here I would to recall that B is certainly a leaf of the section null. B is the section 0, so B is in fact a leaf, and the A is in fact a slice, okay? And the B is in fact a slice, and so we have here our slice. We have here the intersection of the foliation with slice that make those subfoliations here, okay? And so this gives us another way to think about slice and the induced foliations. As you can see here, this intersection of the foliation with slice is a singular Riemannian foliations when we identify the slice with exponential map. We have also this classification that is quite useful for us. We say that a foliation is infinitesimal compact if this infinitesimal foliation is compact. We say that the foliation is infinitesimal homogeneous if this infinitesimal foliation is homogeneous. Okay, that was a little redundant. And F is opt-like if A and B are fulfilled. And this is again the example here, the infinitesimal foliation is homogeneous. And in some classical cases, we know that the holonomy is in fact compact. That is the case when you have B is a Riemannian manifold and E is the tangent space. Then we learn that in this case, the holonomy group is in fact compact, or due to almost, if B is an embedded submanifold and A is the normal space, then again the holonomy group is compacted. So there are a few cases where the holonomy group is compact, And then you have this example of opt-like foliation. So today I want to introduce why I'm so worried about this kind of example. And the main idea, let us have then a preview of what we want to go, in which directions we want to go. So what we want to do today is to see the following. Assume that you have a foliations. Let us think about a foliation with closed leaves, okay? Just to have to simplify a little the things. Take here a tubular neighborhood and restrict your foliation to this tubular neighborhood. An interesting property of a singular Riemannian foliation is that they are saturated. So if you take a small tube, small enough, then your foliations stay there inside. They actually, each leaf belongs to a cylinder. Then we will see that we have a interesting foliation called the linearized foliation. And then you have this holonomy foliation inside. So the structure of every singular Riemannian foliation is like this. Every time you have a foliations, you may restrict in the neighborhood of a leaf. Then you have this guy. This guy is somehow the subfoliation that is the most the maximal infinitesimal homogeneous foliations. That means this guy will have an infinitesimal foliation that is homogeneous, and any other foliation with this property will be contained here. So, and this guy is kind of an intrinsic subfoliation, okay? It is even doesn't depend on the metric. If you change the metric so that you stay with a Riemannian foliation, this guy is preserved, okay? So this contains kind of a topological information. This is stable. This guy, no, this guy, there always exists a connection, and so there will always exist an holonomy foliation inside of each foliation, but this connection may not be unique. So you may have different ways to construct holonomy foliations inside that. Okay, that is our preview. That is what we'll talk today, and that is the reason why we are so interested to talk about holonomy. So before I start to present this scenes, this result here, I would like to start with some language and notation. Please don't be scared. I will try to introduce this concept of groupoid in an example in order, I can present after my talk the formal concept, but let us try to understand the concept in an example. Consider here an Euclidean vector bundle with a compactable connections. I will call holonomy groupoids two manifolds with several maps. So we need two manifolds, a manifold that we'll call the arrow space. And in this example, we think just in all possible parallel transport along a curve. This guy is in fact a submanifold with finite dimension. We think about object space. This is just B. Arrow space, I always put 1 here. Object space, I always put 0 here. Source and target maps. They are maps from the arrow space to the opt space. In our example here, the source space of a parallel transport is just the start point of your curve. The target space of your parallel transport, is just the final the endpoint of your curve. So when you think about groupoid, we think about manifold, sometimes not, Hausdorff, with a B submersion. With a B submersion. So we have two kinds of submersions here. And the idea is elements of G1 should be thinking like arrows. That is the reason of the name. And a groupoid should work like a Lie group. You should be able to compose things. So if you have arrows, and we should be able to compose them. So we need a kind of multiplication. In our case, a multiplication is just the compositions of a parallel transport, and the identity is just a loop, sorry, a curve that is a point, and the inverse can be constructed if we consider the inverse of the curve, okay? Jesus, so far so good. Questions? It's clear what a groupoid of holonomy is. I know this name is not welcome in Riemannian geometry, maybe, but we need this kind of language.
Yes, I think we're doing okay on this end.
So far, so good.
Yep.
Okay. So this guy is quite natural for us in Riemannian geometry. And but to work with holonomy foliation, it's not so good. We have, when you have a groupoid, another example of a groupoid is, for example, when you have a real isometric actions. The people of Utrecht told me, well, I'll always keep this example in mind. It helps a lot. Take just like this. And here you think in an arrow as just gx. This is our arrow now. And so the source of an arrow is just the point. The target of an arrow is then multiply g by x. Okay, so there's another simple example where you have two submersions, and this is clearly a Euclid a manifold. This guy is clearly a manifold. But when we have orbits, when you have this example of an isometric actions, we do have orbits. Orbit for us was this guy. Okay, this is an orbit. We learned that in Riemannian geometry, sometimes even in differential geometry. So this is an orbit. Okay. And how can I translate this guy if I use this fancy language? Well, I could think about take the pre-image of this guy. If I take the pre-image of this guy, I get OG. And then I apply with the target. So this is a fancy way to define an orbit. If for some strange reason, I start to talk about isometric actions like that. The positive aspect of this example is that it suggests to us what should be the definition of an orbit of a groupoid. The orbit of a groupoid will be just like this guy. Here in this example, the orbits are just the bases. So this is an example where you would have kind of homogeneous space because all elements can be achieved from one point to the other. So this kind of, roughly speaking, an homogeneous groupoid. So it is not the right groupoid to describe the holonomy foliation. So we needed to improve this groupoid. And for that, we consider, so this will play essentially the role also of a principal bundle in some sense. And now we will construct, in some sense, the associated bundle. So we start here with our Euclidean vector bundle. And we know that there is a natural way of our previous groupoid acts on this guy. So let us then define what we'll call transformation Lie groupoid of the holonomy representation. Again, as always, we need a space that represents, so if an groupoid is then G1, the arrow space, and there are the points, the G0 space. Source represent the start point of your arrow. Target represent the end point of your arrow. So this guy will be the points of object, the object manifold. This guy here will be the arrow space. It's quite natural. You have an holonomy, a vector, but we want to act this holonomy in this vector, so the source, the foot point of this holonomy should coincide with the foot point of this vector. Now we have source target maps and multiplications in the most natural way. Source is just you take just the vector. Target, you multiply the holonomy by the vector. We act the holonomy in the vector. And the multiplication is just to compose things when they make sense. And the unit inverse can be defined as well here. The advantage now is that if you have the orbit now coincide with the leaves of holonomy foliation. So holonomy foliation is a nice object because it appears in Riemannian geometry. It illustrates a geometric control system. It illustrates infinitesimal homogeneous foliations, and illustrate the Lie groupoid that appears natural in Riemannian geometry, the transformation Lie groupoid of holonomy representation. Sorry for that, that is the name of the scene. But the point is the leaves of the holonomy foliations are in fact orbits, okay? And now finally we can start with our semi-local model. So we want to improve, make more complicated our previous examples of the holonomy foliation. We start again with our Euclidean vector bundle. Here we have a Sasaki metric, but now we will put here in this fiber, in the fiber of your vector bundle, we'll put here some singular Riemannian foliation in Euclidean space. For example, you can put the Rodesque foliation. He hated this name, but anyway, can put here the Rodesque foliation, the foliation construct using Clifford algebras, the foliation that are in some physician's book, like Visual Quantum Mechanics 2. We can put this foliation here. And we need so we put the foliation in fiber. We put a singular Riemannian foliation in this fiber. We need that this foliation in the fiber is invariant by the holonomy of your fiber bundle. So there is some kind of compatibility with this data and this guy. And now so these are the elements that we need. We need a fiber bundle. A fiber bundle. We have here a singular Riemannian foliation in a vector space. And somehow we have compatibility with the holonomy group, such that if I travel from one leaf, I go to the other. At least I should not travel from one leaf to another leaf with a lower dimension. Okay, this should not happen. So and now we talk about these are important data that we need. These are actually the data, and this guy is just a definition. So these are the data, and this guy is a definition. We'll call K0 the maximal connect group of isometries that fix our singular Riemannian foliations. For example, In Clifford foliation, there are Radex foliation that are essentially constructed like this. That essentially construct like this. They take a vector, this is a polynomial, and so they make like this P1 x x a e. This is a generalization of Hopf fibration. You can think about Hopf fibration. By the way, Jesus, have you see this funny way to see Hopf fibrations? You can actually define like this. You take the Pauling matrix and make an applications of C2 to R3. But then this is the Hopf fibration, okay? This guy here. And then when you restrict this, then you go to S2, and this is the better way to describe the submesh that describe the Hopf fibrations using Pauli metrics. Have you saw that at some point?
No, this is new to me entirely.
This is quite new because you may find that this is the way how physicians see Hopf fibrations in C2. When they talk about half quantum bits, they see Hopf fibrations like this, and this is easier to describe. Okay,
I see.
this is easier to describe. And what Radesk do is he takes several other kinds of observers, a Clifford system that is matrix that are orthogonal and symmetric and satisfy our relations that remind us the Clifford algebra, and just write like that. So in Radesk, and very often they don't go to the sphere, they go actually to some disk. Hopf fibration is a very special situation. When we restrict this guy to a sphere, they go just to another sphere. In general, when we restrict this guy to spheres, they may go also inside of the spheres. But this is the Clifford constructions, okay? There is infinite many non-homogeneous examples. Hopf fibrations is included here. All Hopf fibrations with octonials, etc., are included here. And although this guy is not homogeneous, it contains a lot of symmetries inside of the leaves here. The leaves here are just take the pre-image. This would give you our Euclidean singular Riemannian foliations. So these are the ingredients. This is a way to construct. This is a very, 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 very nice paper of Radesk. It was, in fact, his first published paper in GAFA. I remember when he was happy. Oh, I wrote these small calculations. I like that. And then I published in GAFA because the paper is actually very, very, very good. So, and this may illustrate this guy. So now that we have this element, we do the following. Instead to translate vectors, we want to translate an entire leaf. So we have here a fiber. We have here our base. We have inside of our fiber a leaf. And what we do, instead to translate a vector, we translate the entire leaf. When you do that, you get again a singular foliation that turns out to be a singular Riemannian foliation. We can also do something in between. Instead of translating, so you may translate a vector, then you have the holonomy foliation. I cannot write tau. So we may have the holonomy foliation. Let's just write like that. This the holonomy foliation. I may have your original, our foliation is here. You may that means you take this infinitesimal foliation and translate an entire leaf. Then you get a foliation. You can just translate a vector. Then you have a holonomy foliation. But you may have something in between. And something between is this guy. And this guy is take the symmetry, the group of the symmetries of your singular Riemannian foliations, this K, and rotate and translate. Here, as Diego talked, he was talking about some strange people who may use non-connected leaves. He was talking about me and Radeska. Sometimes you need to do that, even in actions. Isotropic group doesn't need to have one connect component, okay? But anyway, this guy fix leaves. That means he may send one leaf to the other leaf with the same dimensions. You rotate and then translate. So this guy is rotate and translate. This give this subfoliation here. This guy is just translate one vector, and this guy, while you take a leaf in your fiber and translate everything. So, and why I want to make your life even worse? Because this model actually describe everything. If you have a singular Riemannian foliation with closed leaves, on a complete Riemannian manifold, actually something even a little generalized than this, and consider a fixed singular leaf B here, then for a small tubular neighborhood, for small tubular neighborhoods are always foliated. So you have the following. First, your foliation stay inside, like isometric actions. You have the opts stay there, the foliations stay there. And the interesting thing, this guy here is foliated diffeomorphic to the item A of your model. So you always can think about a foliation like that. You take an infinitesimal leaf and translate by an holonomy. So yesterday, Diego was talking about holonomy. You can think about the holonomy that Diego talked yesterday like that. Actually, what he was talking is consider this holonomy and then pass the quotient. But anyway, it comes from a real holonomy of Riemannian geometry. You just have to pass the quotient, but yes, it is a real holonomy. And the second thing that is interesting, there is a maximal infinitesimal homogeneous subfoliation inside your foliation, this FL. And this guy comes from the item B of our model. This guy is this guy, okay? So you rotate and translate. And this guy is somehow very, very, very important. For several reasons, we will see this today. I'll remark, maybe you are not interested in those kind of things, but this guy are opts of a Lie groupoid that is essentially that the groupoid that I told you. Not that, it's a kind of generalizations, but anyway, this guy comes from a Lie groupoid. What help us to use the theory of a Lie groupoid? We should say a few words about that later. So this is our first model, and today we'll see applications of this model, okay? There is a second model, of course, and assume what happens if your foliation has non-closed leaves. You still have a model. I will not concentrate in this topic today, but I will just say that we have a model. So if you have a singular Riemannian foliations, B is a closed saturated manifold. For example, B, you can think in B as the closure of L. Then the foliations and these linear foliations are again described by a model. The difference is instead to talk about connections and parallel transport, you may have to talk about what we call partial connections, where just allowed to travel, make parallel transport, but not on entire B, just along a foliation that is inside of this B. But I'm still thinking this is quite important, special for operator theory. So sometimes this just happens. And anyway, this describes the whole situation when you have a singular Riemannian foliation with this sort of dynamic behavior with non-closed leaves. You still have a semi-local model. This guy is again opt of a Lie groupoid, and again, you have a situation that reminds us the situation of opts when you have torque actions like what Jesus told us yesterday. Okay, he told us something quite more interesting and complicated. He was doing actions in metric space. But anyway, if you have a torque actions, you may think about the irrational flow. And the one advantage of the irrational flow, if you think about irrational flow, it's a sound a crazy actions. It is not Hausdorff, but you can take the closure of the group, and the closure of the group give you the then you just work with the closure of the group and everything is fine. So something happens again in the theory of the foliations. So there is a proper Lie groupoid over a tubular neighborhood whose opts are the leaves of this guy. This guy is dense in the subgroupoid. Why we are interested in do such kind of things? This was behind of this old conjecture that I told you last time. There was the so-called the Molyneux conjecture proved by Rodesky and I. And when you proved that, we started to see that there was something strange inside of this guy. That we proved that we have proved that if you take the closure of each leaf, then the partition turns out to be a singular Riemannian foliation. And we kind of see that there was a subfoliation that we started to call it. So this foliation appears first in the paper of Rodesky and I. We start to see that this kind of foliations contain the all dynamical behavior of your foliation. So that guy was quite important to prove the Molyneux conjectures and kind of to describe the dynamical behavior of F. It was a little more complicated than that, but what I'm saying is true if you have infinitesimal compact foliation. Otherwise, you have to talk about a third kind of subfoliations that I don't want to show you today. But if you are talking about infinitesimal compact, what I'm saying is 100% true, that this guy contains all dynamical behavior. So if you are trying to understand things that depend on the dynamical behavior, you need to deal with this guy. We needed to deal with this guy to understand this result. And we will see this in an applications today. So that is why I'm talking about this linear guy. Jesus, how are we? So far, so good. You have your questions?
Yeah, actually, I had a question from these theorems. So, would it be fair to say that because of these three theorems, then a foliation can be seen sort of like a local action, but you don't really have a
Yes,
Lie
yes,
group,
yes, 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 yes,
it's just
yes,
a
yes,
groupoid,
yes.
right? But
It is the spirit of the things. Although you cannot say, we still don't even know. For codimension 1, these isoparametric foliations, the Ferencz-Caster-Münster, and we don't know if the Rodesky foliation comes from an Lie groupoid. But we know that there is a kind of generalized action, and these generalized actions, the so-called groupoids, they describe the entire dynamic of the behavior of F, and it is inside of F. So the intuition is when you take the F in the tubular neighborhood, there is a kind of generalized action, and
Yes.
this is good. And these generalized actions describe two things. If your foliation has non-closed leaves, it describes the dynamical behavior of your foliation. If your foliation still has closed leaves, so it's not important. No, it is important to do analysis.
Yeah.
I try to talk about that because the Lie group is very, very, very nice.
Yeah.
We can do several things with the Lie groups. And so there is a kind source of generalized actions that it's not entire foliation, but it is inside. And this is roughly the idea.
Okay,
Yeah.
this reminds me a lot of I'm sure you know this concept of F structure, right? And
Yes,
the
yes,
sheet
yes.
and like this reminds me a lot of this type of construction. So for
Yes, yes.
example,
Yes, please, please.
is there like a super big groupoid that contains all of these local groupoids and maybe like a sheaf that acts locally and you recover like the tubular neighborhoods of the foliation,
That
something.
is one of the questions of the area. We
Ah,
don't know and have any hope to have just a groupoid that describe all the things, but we
okay.
hope to have a kind of sheaf that describe the entire quotient information. In fact,
Okay.
this is in the survey. We have a survey. I have a survey with the Francisco Caramelo about killing foliations. So
Mhm.
if you have a tubular neighborhood, you can think about this guy, for example, you take the slice quotient with the infinitesimal foliation. This gives you a metric space. I will talk an example where this infinitesimal foliation is compact, but your leaves are not, okay? So
Okay.
instead to consider an orbifold, you start to consider this union of a metric space, and then isometries from one metric space to the other. So you have kind of a generalization of orbifolds. You have a metric space, diffeomorphisms from one metric space to the other. This guy is the slice quotient with the isotropic foliation that comes from of your slice, and the
Mm-hmm.
diffeomorphisms here. So in
Nice.
some sense, yes, we do have sheaves that describe a lot of things. This already exists, or at least exist in our desk. I don't know if it is existing in archive. I think yes, in this preprinting archive, I wrote that in a preprinting archive, and we never published that.
I see.
But we intended to do. So yes, there is something in our desk and archive about shifts of those things. And that is
Nice.
the reason why Caramelo is doing equivariant cohomology for
Mm.
singular Riemannian foliation. So you may think about infinitesimal actions in metric spaces and start to do equivariant cohomology. Yes, yes.
That's nice. That's very interesting. All right. Thank you. Thank you so much.
Yes. So I will do the following. I will later I will try to give an idea of this guy, maybe in 2 minutes, just to say that it has everything to do with the lecture 1 and 2. But instead to do that, I will like to jump to some applications. I think this is more important, and to see how those models work. Okay, so the first applications that we have is in mean curvature flow. Luis told us a little about that, a lot of about that. I will not do so good work as Luis, but I intend to do mean curvature flows for actions, for example. So what is a mean curvature flow? You have an immersion, you have a smooth family of immersions, okay? And a mean curvature flow is a family of those immersions that fulfill this equation where this guy is the mean curvature flow of your immersion. I will be considering immersions without self-intersections, okay? So I'm do some kind of abuse of notations, identifying the image of your immersions with the immersion itself. It will not cause problem for me because I'm considering special situations of mean curvature flow. So, so, so this is a mean curvature flow. We want to travel along the mean curvature and see what happens. And we can do that. And this is the picture that we should have in mind when you start with an orbit. If you start with an orbit of an isometric actions, if you start with an orbit of an isometric actions, we know, for example, you can see this in my book with Renato Bettiol. It's not difficult to see that if you start here, your start L is a principal orbit. It's a principal orbit. Then the mean curvature flow, the mean curvature vector field is basic. So at least nearby, you can travel this complicated scene. This is a partial differential equation. This guy you can project to a vector field here that turns out to be then a vector field in a manifold if you are just looking in the regular part of your orbits. What happens if you are looking also in the singular part? Well, if you are looking in the singular part, you have a strange case. You have a metric space MG, and you are working with the vector fields in a metric space, and they may be collapsed. There may be different situations. Let me start to make a picture, and this give you time to, but this is kind of problem that we are interested in now. You are interested to understand the mean curvature flow of actions and generalization of actions. Since, for example, in actions, the mean curvature vector field is basic, is G invariant. When you are traveling along the mean curvature flow, you go from one leaf to the other, and this means you can here project the situations. So we want to try to generalize this kind of things. A singular Riemannian foliation, we'll call it a generalized isoparametric foliation if the mean curvature vector field is based in the principal stratum. This is sufficient to work with it. And the first example that you should have in mind is our opts, a partition of isometric actions, isoparametric foliation, that is polar foliations that are generalized isoparametric foliations. There are Dex foliations, the Clifford foliations in Euclidean space. Actually, one can prove, and Radesk and I proved in the series of papers that we wrote, that every singular Riemannian foliations in Euclidean spaces has these properties. Examples of the Holonomy foliation also have these properties. So it is not true that every singular Riemannian foliation is generalized isoparametric, but we'll have a lot of examples. And in fact, if you are in a neighborhood of a B, since you have this model, it is true that since every Holonomy foliations and the scenes in the model one are generalized isoparametric, at least in the neighborhood of a leaf, the singular Riemannian foliations admit a metric that make it generalized isoparametric. So this is the kind of things that we want to do. And again, not to delay everything, I want to state a result that use, for example, our connection, the holonomy foliation. The existence of the holonomy foliation has allowed Leonardo, Leonardo, C, G, Icaro, and I to generalize a previous result of Radesk and I that generalize a previous result of Turner published in Duke. Turner was studying isoparametric foliations in sphere. What was the behavior of the mean curvature flow of isoparametric foliations in sphere? Radesk and I then published a paper about isoparametric mean curvature flow of mean curvature flow of generalized isoparametric foliations in every compact manifolds. It starts with a very, very nice idea of Radesk. He's the main author of this paper. He starts with the idea that works for a sphere, and then we work together to generalize that for all compact manifolds. I think this is a very nice paper. That is basic of attractions, metric. It is very nice idea to deal with the comparison results and quotients. Very nice paper. Everything starting in sphere. But the point was, what happens if M is not compact? And when are dealing with the isoparametric foliations already in symmetric space, there is a lot of examples of foliations in non-compact case. And even if you are near a tubular neighborhood, what happens? In this new paper, we can give explanations of what happens in non-compact cases, essentially because we have these holonomy foliations. This tau allow us to generalize the previous results with Marco in the tubular neighborhood or in the entire manifold if you extra assume that this guy is compact. But if you just are interested to understand the examples that people have in Hadamard space, this paper may help. And they say essentially the following. A leaf converts to a singular leaf in the sense of the quotient. And if the curvature of M is bounded and the shape operator along each leaf is bounded, that happens, for example, when you have actions, then given a point, your mean curvature flow actually converges. And the conversion is the best possible kind of conversion. It's called the type 1. It essentially say that it behaves like orbits, like the mean curvature flow of cylinders and the spheres. It explode, but explode in a nice way. And this kind of result use the holonomy, use the tau. The tau was quite important to relate the geometry of M with the geometry of the semi-local model. And it allows us to make this kind of estimative. So this is, I believe this is a nice way to illustrate how important the connections are. And I kind of have 3 or 4 minutes, but I think this will be enough. I love this kind of, so this is the infinite, this is the case when you have leaves with the compact leaves. We have also a mod results when you start with the non-closed leaves. When you have non-closed leaves, then you have a dynamical problem. And it's not true that the mean curvature of the closure coincides with the mean curvature of the leaves, because you may have something that is inside of the leaf. So then you have to apply the semi-local model 2 to start the mean curvature flow of leaves that are not closed. So dynamical problems, you need the model 2. So, and if you want to have a picture in mind, I love this picture here. You may think conjugation actions. For example, in the book with Renato and I, and you may think what happens in the mean curvature flow in our quotient space. Our quotient space here, we learned that in Lie group theory is just this triangle here. And what happens if you in the barycenter stay here, otherwise you go to the vertex, and there is some point where you go to the walls. So you understand quite well what happens in this picture here. So, but this is a kind of result that apply as semi-local model 1, and because if it includes vector fields and dynamic behavior in metric space, basis of attractions and things like that, it's not true that Molyneux conjectures, this theorem that we proved, solve everything. We needed to have a result for mean curvature flows for non-compact foliations, and we do have this result. But let me talk about something that now we just need model 1, because we are dealing with the integrations and the calculus of variations, Yamabe problem, and things like that. My last 2 minutes, consider a linear function, and here it's quite important, these generalized actions, okay? Here it was important, the connection tau, and here it's quite important, this Lie groupoid structure. Consider here a linear functional that it smooth functions, and it is we say it is symmetric if, although F is not basic, if I compose F with the flow of the so-called the linearized vector fields that generate this linear foliation, the maximal infinitesimal homogeneous foliations, then it works. When this works, we call that our linear functional symmetric. And we have what we call generalizations of symmetric critical principle of Palais that say the following: if you have a symmetric linear foliation functional, and if your functional is 0 for basic function, then it is 0 for all functions. This allows us to start when dealing with the calculus of variations, and although we are dealing with all functions in the space, if you are dealing with the calculus of variations, so you are dealing with the critical points of action like that, you have a problem like this with a Lagrangian that is basic, that in this component here, x and the y give you the same value for your Lagrangian when the points below to L. If you are dealing with this kind of problem, that is Yamabe problem, that is P-Laplacian, that is P-Kirchhoff problem. So if you are dealing with the calculus of variations with this guy, then your L take this form. And so the question is, when this L is symmetric in our sense, this guy is symmetric in some cases, for example, in semi-local model, in isoparametric foliations. In fact, we don't need this guy, but okay, I put here just to make my exposition more clear. So isoparametric foliations, polar foliations, we have this. So the point is, when I'm doing analysis, we may have in Yamabe problem, P-Laplacian operators. We may have to deal with this critical index of Sobolev, critical exponential numbers that destroy the embedding of the Sobolev space. So if you have the luck to have action a Lagrangian here that is basic, then you can reduce your problem to study basic functions. And since you reduce your problem to study basic functions, we have no longer to deal with this problem of the embedding of the Sobolev space. So you can start to getting a few results. This is just examples. You have if you have your connection is flat, then you have you can solve Sazak problems in fiber bundles. This is a corollary, but actually Diego proved a better result. Okay, but I just want to illustrate how to apply the principles of symmetry. But this is a particular case of what Diego has proved. If your scalar is basic and you have a isoparametric foliation, then it's okay. Then you have then you can solve Yamabe problem in such a way that the leaves are still equidistant. And what my point is, to deal with this kind of problems, we needed to prove this result. And this result involves to integrate over source of Lie groupoids. So use the technology of Lie groupoids to have this principle. And nowadays we are applying this principle to study critical points of variational calculus where this Lagrangian is symmetric. For example, for isometric foliations, so we may have Yamabe problem, P Laplacian problems, P Kirchhoff problems. Kirchhoff problem is this kind of muscle of robots, but I will not have time to talk about that. So that is just to say that, yes, the lectures make sense. We need connections and we need groupoid. Connections allow us to deal with the bounded geometry, and the groupoids allow to integrate, like we like to integrate over a group to make a function, a base function. We can integrate over a groupoid, and using this average, we can actually do some calculus of variations. But that's okay, Jesus. I think my time is over, but I hope to give some flavor, some key ideas to read our papers. I don't know. Thank you, Jesus.
All right, thank you very much for this wonderful lecture.
Okay. And if the people have questions, they can send you to me. I can answer in email. I don't want to delay the talk. You may stop sharing the screen, man.
Okay, yes.
I don't know how to do that.
Definitely, I can do that on this end, and I think I speak for all of us here and in the chat to say that this was such a wonderful mini course, which certainly
I have
it really sparked my curiosity.
Before I end that, so thank you very much. Feliz cumpleaños, parabéns, feliz aniversário.
All right, awesome. So thank you very much again, Professor.